So the last talk of the day is by Damian Osajda from Copenhagen, who is going to tell us about systolic groups. Exactly.
Exactly. It makes sense, I believe. I mean, my talk too. But so, so I should start. I should start with motivation. I mean, sometimes people start with motivation. Let me start with meta motivation first. So I was reading like some time ago an article in New York Times about the guy who fell into delusional loop with his chatbot friend. I mean, it was about this chatbot friend. His name was Lawrence. He was convincing him that the chronometrics that the guy invented. The guy, it was not me, the guy. And he was not a mathematician, and he was. I mean, Lawrence convinced him that that this was a great theory. Of course, it was kind of not great theory. I mean, and you can, you know, there is the usual reaction is that it's so stupid and blah blah blah. But for me, it was striking how supportive, how kind, how encouraging the friend was. So I asked Sophie, my friend, my new friend, about my research. So she said, for example, it extends the boundary of the current knowledge in meaningful ways. So just so you know, just so you know what you are experiencing today. I mean, I expected something more striking. But okay. But Sophie is great still. Okay. So here is the motivation, like the real motivation now. This is the joint work with Martin Blufstein, Victor Chapoy, and Huaitao Goi. Huaitao is my student in Copenhagen. He is here. Martin was our postdoc. Okay, so here is the motivation. So I will, throughout the talk, I will consider mostly a group, finitely generated group. So this is finite. And then this group, and then we have a word metric coming from this generating set. And we can treat the group as a metric space. So this group with a metric space, with a metric, word metric, is a metric space. And now, I mean, in geometry groups, you want to understand often the geometry of groups. And it happens, I mean, it appears that one nice way of understanding geometry, or one nice feature of a geometry, is when you have a coarse embedding. So let me write F. Coarse embedding into a Hilbert space. So if you manage to embed your space, your metric space, into Hilbert space, it gives you a lot of information about the geometry. So coarse here means, let me just write it quickly. Coarse means that the distance in this Hilbert space between images is bound both ways by some functions. I mean, they should be growing functions, whatever, of the distances in the original space. So in this case, in Sx, well, okay, I should use G and H. So that's just it. Just there exist two functions. They should grow, whatever. But you know, the distance between images is only like uniformly kind of bounded by the distance of the pre-images. Okay. That's a coarse embedding. And it happens that this gives you a lot of information already, whatever these functions are. I mean, whatever these functions are. So one big results were that this implies the so-called coarse Baum-Kohn conjecture. So this conjecture makes sense for metric spaces, but I want to stay in the realm of groups for some reason, and but this makes also sense for groups as metric spaces, and for groups, for example, it implies the Novikov conjecture, actually strong Novikov conjecture. So I do not want to explain this. What's that? I mean, but at least those are fancy sounding names, right? So, and I just want to tell you that having such thing, I mean, having such a control on the geometry gives you already something. And then, so it was Guliang Yu actually who proved that that embedding into Hilbert space implies this. And actually, so now the question is, when can we embed the group into Hilbert space, like coarsely? This is not really embedding. It's called coarse embedding, but this is up to this. I mean, it's in this sense. Okay. So, and actually, there is a nice property that Guo Lianqiu invented, implying this coarse embeddability. I will call it coarse embeddability for short. It means coarse embeddability into Hilbert space. And this is the so-called Guo Lianqiu, it's often referred like this, property A. And this is, and he formulated it in a coarse geometric language. I will present you the definition later. But for a moment, let me just treat it as some property. So I will say like the G has, if G has used property A, then G is coarsely embeddable into Hilbert space. But actually, it happens that this property seems to be of interest on its own, because it has many equivalent formulations for group. And so let me say, so this is like coarse geometric property. There is a property saying that G is the so-called exact, meaning that it's C-star reduced algebra is exact. It's kind of functional analysis property, analytic property, and it's also equivalent for a group. Let's say for finitely generated group, it's also equivalent to G being boundary amenable. Which means that G admits amenable, topologically amenable action on a compact, non-empty space. So the property itself, you know, I mean, so it's not, it was around 2000 when he proved this and introduced this, but so it's no surprise that this property started to live kind of on its own. And people who are interested in this are still interested in this. So my talk will be about this this property for groups. And this exact is this exact there. Okay, so this is why I say the title makes some sense. Okay, so this is some property, and I will tell you in a moment what's that. But first of all, still like having it as a black box kind of this property, let me say that this property can be thought of as kind of weak amenability. So, and also some people also say like non-equivariant amenability or coarse amenability. Once again, this makes sense for, actually the property A makes sense for metric spaces, not necessary for groups as amenability. Okay, so it's not maybe surprising because amenability, it has many equivalent formulations. There is actually more, even analytic ones. There is that von Neumann algebra of the group is nuclear and so on. Okay, so there is this property that we are interested in today. So here are some examples and non-examples. So let's say groups. So just examples. So groups. So non-exact groups. I will probably switch between boundary amenable, exact, and property A. So, but now you know all of them are equivalent. So you will excuse me. Or anyway, I will do it. So non-exact, exact groups. So there are non-exact groups. And actually there are two constructions. So one is the Gromov random monster group. So this is a construction by you know who. And then there are small cancellation groups, or graphical small cancellation groups. They are different groups. And now you know this is construction by who. So those are basically two constructions. I mean, there are derivatives of this construction, but basically you have this. By the way, here is a personal remark, my personal remark. So I first heard about this, I believe in 2007, around 2007, exactly from Misha Kapovich. I mean, so you know that he knows everything, and he knows a lot about different things, and actually he told me about these groups. I mean, this was new then. I mean, there was still a lot of discussion about this group. And actually, he told me about this in context of systolic groups. I don't want to get into details why, but this is nice kind of loop. And so, yeah. And since then, I've been interested in these groups. Okay. So those are non-exact groups. And about exact groups, basically all the rest are exact. So we believe that, I mean, most groups that we meet on a regular basis, like commuting, stuff like this, are exact. But it's not shown for all the groups. So here are some examples, because I want to, I don't know, flatter people in the audience. And I know it can end up that I offend someone. So please be, be like Sophie. Okay. So hyperbolic groups, of course. I mean Gromov hyperbolic groups. And this is all the result by Adams. And then it has many, of course, many proofs. And then there are cat-zero cubical groups. And this is also important. And also, I'm not sure if I list everything, but I basically list all the known things that I found, but definitely all the relevant ones. So cat-zero cubical, and there are several papers, and this goes to works of, I mean, in different configuration of Brodsky, Campbell, Niblo. So Graham is here, and he's the expert, I believe, here for this. So I mean, just Günther, yeah, I believe, and Wright. So I mean, because this was the first proof for cat-zero cubical for compact groups, and then for other groups, and then also for cat-zero cubical complexes actually. So and then mapping class group, and this is Hammenstadt and Kida. I mean independently, Kida, Yoshikata Kida, and then there is Autefen. And this is Bestvina, Girardel, and Aube, Camille Aube. And then there is, okay, and then recently, it is very relevant to my talk, and there are two-dimensional Artin groups of hyperbolic type. And this is Jingin Huang. Okay, first Camille Aube and Jingin Huang. And we had also some small paper about two-dimensional systolic, and I will repeat it kind of. Systolic, so this is Nima Hoda and myself. Okay, and that's basically it. I mean, so for example, there is an open question whether cat-zero groups are exact. So question, are cat-zero groups exact?
Are there any permanence properties, like descending to subgroups or finding them subgroups?
Yes. So this is, okay, yes, I didn't say that, but this is coarsely invariant property. In particular, I mean, subgroup. I mean, if you have coarse and if you have, this is property, once again, I'm sorry, I will be messing here, but just to give you a full answer, this is property of metric spaces. If you have a metric space that coarsely embeds into property A space, it has property A. So in particular here, I can say cat-zero groups, meaning group acting properly, because proper action gives you coarse embedding. So it's whatever, but it's not even known for compact cat-zero groups. Okay, so now I will state the theorem, the main theorem, and then I will explain all the notions and give you some proofs, hopefully. So here is our theorem. I mean, of those three authors plus me. So our theorem is that. So Blufstein, Chapoy, Hoytaogui, and myself is that uniformly locally finite fit systolic complexes have property A, use property A. So this is the first theorem, and there are no groups, I mean, to some extent. But so actually our interest was because of the following corollaries. So corollary 1 is that large type Artin groups are exact. And actually, we do it for a bigger class than large type, a slightly bigger, which is almost large type Artin groups. And the second class that we know that gives a new class of groups with property A are some small cancellation groups. And so it says that finitely presented, let's say even graphical, whatever it means, but you can think small cancellation C3, T6, small cancellation groups are exact. And those are kind of immediate corollary. Let me just say quickly, and then I will maybe extend it. So simply large type Artin groups by the work of Jingin Huang and myself act on systolic complexes, and we actually show that there are fit those systolic complexes, and also we show that these groups act on fit systolic complexes nicely. So those are two corollaries of this that were kind of our motivation, and we believe there is more. There are more groups fitting into, that you can prove, that you can show exactness using our result, and yeah, we believe it develops some new tools. Okay.
It's finitely presented.
Yes, I say finitely presented because, okay, first of all, for non-finitely presented graphical small cancellation groups can give you these examples, for example, these non-exact examples, in fact. Yeah, by the way, this is more, those two examples give you more than non-exact. They give you also non-coarsely embeddable into Hilbert space. There is no, the reverse implication is not true. But those are that strong, those two examples. So graphical small cancellation, infinitely presented doesn't go well with property A. I do not know if C3, T6, because those examples are C6, whatever it means. But I do not know if this also goes wrong, but for our approach, we need finitely presented because we wanted the complex to be uniformly locally finite, the complex that you get. So this is why. And any other questions? Okay, so let me now do some math, tell you some definitions. So we say that a metric space, and I will restrict here to, let's say, discrete metric space. So definition. So if X is discrete has property A, I should do some splitting, right? If the following happens. So as I told you, there are many equivalent definitions, similarly as in the case of amenability. I give you actually the original definition of U. Okay, so it's a bit different than original, just a small detail. So if for every epsilon and r, those are some constant that you pick, this should be small, this should be big, there exist finite sets for every x in x. So that this definition should be thought of as an analog of Fellner condition for amenability. Okay, so we have this finite set, and actually those are finite finite subsets. This is why this space is discrete. So those are finite. And actually, those are subsets of not only x, but x times n natural numbers. Yeah, I just learned that from Graham, Niblo, with collaborators, they have another definition which you can forget about this n, but this n is natural in a sense. This n is natural for coarse invariance of this property. But it can be even more similar to Fellner sequence, to Fellner definition. Okay, so that there exists this. So for every x, you pick some set, like Fellner set, and also there exists m that bounds kind of diameter of this set. So we say that every ax is contained in, so such that every ax is contained in the ball of radius m around x times n. So this is important. This is like bound. This is this bound. And second, that you have, like in Fellner property, you have that the difference, symmetric difference between sets for close points. So if the points are close, then the symmetric difference is small, but of course you take to have relative symmetric difference, so like ax and ay. So they are small. They differ by small amount, but of course relative. Right? So it reminds the definition with Fellner set. The Fellner set is that you move it a bit, and you attach the big set, bigger and bigger set to elements of a group, and then when you pick it, move it a bit, the difference is small, right? So that's the definition. So now you know it. And yeah, and as I said, there are other. There is many definitions of property A even for metric space. And in case of group, it also has some other incarnations, like analytical or dynamical and some others. Okay? Yes?
Can you say what's the role of the natural complement there?
Okay, so let me, let me just say that another definition that you can easily derive from this is that instead of sets, you take the functions, let's say finitely supported functions. So this is like the value. It can be thought as a value. And then here you take the difference, the sub-difference of the functions. And so if you try to prove this is important for coarse invariance. If you have two spaces that are coarsely equivalent, meaning that there is coarse embedding one into another, then this property is preserved, the property A. So let me say this. I will not present you the proof because I'm not prepared. Also, I think it's not there. Okay, does it make sense? So this is definition. This is the explanation, I believe, of this last part of title exactly. So let me now explain for which groups we prove this property. So this fits systolic. So so systolic complexes are kind of non-positively curved complexes in a combinatorial way. But let me give you a precise definition, precise but useless. Not useless, but not intuitive. Or okay, you will see. So first of all, a graph is bridged. So this is definition of bridged. If isometric cycles have length 3. So this is I'm not finished yet. So what it means? No, isometric cycle means that if you have a cycle in a graph, cycle is let's say simple subgraph. Then you can compute the distance in the cycle, right? Like distance of those two guys is those two vertices is 2. But you also can compute the distance inside the graph if it's inside the graph itself, if the cycle is a subgraph, right? So it can happen, for example, that there is an edge in the graph, and this cycle is not isometric, okay? So this condition tells you that the only isometric ones are triangles. So you can play now. I mean, this is exercise for those who will be bored. Okay. You can play now about a bit with this, and for example, if you have a 4 cycle, like the same as here, it means that it has a diagonal, right? And now if you have 5 cycle, it means that it has some diagonal also, and then this has diagonal. Okay, so this is the simple definition of bridge graph. It is global, though. I mean, you have to check all the cycles, even long cycles, right? However, actually, it gives rise to a local to global property. So let me first tell, I mean, for graphs, it's hard to say about local. So let me first say that a simplicial complex, a flag simplicial complex is systolic if its one skeleton is bridged. And the story is that these bridged graphs were studied for a long time, since 80s or whatever, in graph theory, in metric graph theory. So there are names like Chapoy, our co-author, and some others, actually. It was independently discovered. And then the systolic complexes were introduced by Haglund and Januszkiewicz and Świątkowski into the group theory. And you know, the point is that basically those are the same objects. Flag simplicial complex means the simplicial complex in which whenever you see a click full graph, it means that the corresponding simplex is there. Okay? So flag simplicial complexes are totally determined by their one skeleton. So bridge graphs and systolic complexes are the same. Okay? But here, with having this topology now, I mean, you fill the many loops, you see that there is some kind of non-positive curvature. In particular, the systolic complexes or bridge graphs can be defined, can be characterized locally. So a flag simplicial complex is systolic whenever it satisfies some local conditions. Actually, the local conditions is basically the same as here, that the links are of this type, kind of, and then it's simply connected. So this is really like Carte and Adamar for non-positive curvature. So this is why we think that they are non-positively curved, and in many ways, such systolic complexes behave like non-positively curved. And they are kind of simplicial analogs in some sense of cat-0 cubical complexes, where you have also local condition together with simple connectedness give you some non-positive curvature, kind of. In fact, you can put the cat-0 metric, but even without cat-0 metric, you can do a lot of geometry. You should do. Okay? So that's it. So there is some, I will not go in further, but there are some, there is this notion of systolic complex which should be thought as non-positive curvature, and there are groups acting on such complexes. So these complexes were useful mostly for constructing groups with nice properties, but there are actually also complexes, classical groups acting on such complexes. Any questions? So those are the definitions. I think now all the definitions, I didn't say what's fit, but I think the systolic groups exactly is already explained. So, any questions? Of course, you should disturb me anyway, anytime. Maybe not anyway. Does it make sense? Okay. So now I will explain fit. For this, I need some. I need some property of systolic complexes, so I will just tell you the result. Maybe before this, let me just note something, because I will use this picture. So the very simple example, but non-trivial in a sense, and kind of generic example of systolic complex is the regular tessellation by regular triangulation of Euclidean plane. So this is systolic. So you can check it. I mean, like, okay. And the point is here that the links have graph 6. So this is where the name systolic comes from. I don't want to get into this. And we'll use this picture, the picture of systolic plane. I will call it systolic plane. Okay, so here is some property of systolic plane that, of systolic complex that also gives me the some notation. So some time ago, so we were proving many things about systolic complexes and systolic groups, and one, let's say, lemma that we proved with Piotr Krzytycki at some point for totally different reasons is the following, that if X is systolic, then the level set so level sets are just, so I will call LK, so level set between X and Y. This is the intersection of balls. So in systolic complex, I mean in simplicial complex, I take the metric on the set of vertices, just a path metric coming from one skeleton. This is my metric, and then I can think, for example, that I take the induced complex induced by the ball in vertices, in vertex set. So if you have K, BK, this is K ball around X, and you intersect it with ball of complementary radius D minus K in Y, where D is the distance between X and Y. Okay? So you just have, so let's say, I will also introduce some terminology. So it was already told what are kind of intervals in metric space. So it was probably in Ursula's talk. So when you have a metric space, then you have this between, as you say that Z is between X and Y, or in the interval when this distance plus this distance is this distance, right? So in many spaces, in particular, if you think about this systolic plane, we already actually saw this picture. So the interval between vertices looks like we saw in Finsler metric. So this is the interval. So there are many geodesics, and then so you can let me draw like interval like this. And then level set is, those are complementary balls. So this is like a section of the interval, right? So this is like, okay, this is a distance, okay? So what we proved is that level sets, okay, in systolic complexes are 1-2 quasi-isometric, are 1-2 quasi-trees. So there are quasi-isometric 2 trees with multiplicative constant 1 and additive constant 2. Actually, we show more, we show precisely what they are. They are the so-called chordal graphs. So graphs without any isometric cycles. So, but this is how we should think about this form. So here's an example. Here's the picture that you should have in mind. So think about intervals in systolic plane. So they basically look like some figure like this. Okay, where you go like this way. So this is interval between X and Y, whatever. And then somehow here you have interval, okay? And I told you that interval is kind of quasi-tree, so you should think that, that interval looks like something like this. This is perpendicular, right? Sorry for that. Okay, that makes sense? So that's it. And now, this I need for the definition of fit. So there are quasi-trees in all systolic complexes, and now we say that a systolic complex is fit if there exist constant B and C such that all, okay, actually, yeah, all level sets are BC quasi-lines. So there is no this essential branching. Okay, so indeed they really look like kind of fat line, just a line. Okay, and what we will need, I mean, why we need it, you will see it in the proof, but it's just because trees grow exponentially, lines grow linearly. Okay, and that's it. Does that make sense?
You assume that the complex is locally finite?
Where I mean, in the theorem I say uniformly locally finite. No, in the proposition I don't, because I told you there are actually we know more. There are very thin graphs. There are the so-called chordal graphs. It means there are infinitely systolic if you know this notation, or there are no induced cycles, except all induced cycles. I mean, the only induced cycles have length 3. They are very thin. For simplicial complexes, you are basically allowed only to glue simplices in a tree-like way, kind of. There is nothing about local finiteness. Okay? Okay, so this is fit. So now you understand the title. Okay? Any questions? Good. So now I will present you the proof. Nearly complete proof, and then maybe, and if time permits, I will also explain the corollaries, and maybe you remark what's further. So the proof. So the proof relies on the. I mean, okay. So many of these results about exactness actually rely on this action on hyperbolic space. I mean, if you have action on hyperbolic space, there are some tricks. And then there are some tools for proving some other tools for proving exactness. For example, for this K0 cubical complexes, they have to come up with some new techniques. And then actually there is one more technique that was developed, I mean, one technical thing that was developed recently or later. So they call it proposition, so I will call it proposition. So there is a condition by Jan Spakula and Nick Wright, a technical device to prove property A for uniformly locally finite graphs. Let's say for uniformly locally finite discrete spaces. And actually they used it to reprove in a, let's say, easy way K0 property A for K0 cubical complexes, and also for some median, coarse median spaces, some nice coarse median spaces. So here's the proposition. So X is a discrete metric space or locally finite graph, uniform locally finite graph. So this is uniformly locally finite. So it has property A if there exists, and this proposition is kind of, you will see that it has a lot to do with this definition of U in a way. I mean, it's the same spirit. So again, you want to assign some finite sets with some invariance property, kind of. So here we say that there exist sets of the form XKL, where this X is an element of X. This K, this L is a natural. So this is just a technical device. And this K is also natural up to 3L. So this is number from 1 up to 3L. it simply comes up into the proof, in the proof. So those are subset of X. So instead of assigning this AX, I assign now subsets of X, but with some other properties. Okay, so such that, and I want to state this because, I mean, having this, you will kind of immediately see, I mean, it will be nearly the full proof. I can give nearly the full proof. And actually also you will see, if you reinterpret it, you will also see another proof for cat-zero cubical complex, actually the proof of Spakula and Tribe. So I think it's just interesting. So I mean, you know, we should somehow mimic the properties of them. So one is this, they are kind of bounded. So for every L, there exists RL such that these sets are not too big. So R around X, ball of radius RL around X. Then second is kind of invariance. So if you have the set at X with this parameter K minus distance from X to Y, and then L, then it's contained in the intersection of sets for X with KL and Y with KL. So this is kind of like, you know, like this. If you move them, they are kind of small. And similarly, symmetrically, if you have S, X, KL, union S, Y, KL, this is contained in the set around X with the parameter, this, again, this middle parameter K plus dxy. And the third one is important, kind of, actually, that corresponds to this fitness restrictions that we have. There exists a function P, it's a function, such that the cardinality of xkl is bounded by P of L, and this function doesn't grow too fast. So you have P of L to 1 over L tends to 1, where L tends to infinity. So this is like, I mean, you should think, you know, it behaves like polynomially. Okay? The growth of this is polynomial. Okay, does that make sense? So now, I mean, now I want to show you how we construct simply those sets for systolic groups, for systolic complexes, and actually, and that it works for fit systolic complexes. So X is, let's say, systolic for a moment, even not fit systolic, but just systolic. And then we construct of this SXKL. And this construction, I will draw it, I hope, in the way that will also work for cat-zero cubical complexes, because the idea is the same. Just we have to prove some properties. So here it was what you do. So there is no, just to be clear, there is no any equivariance. Like property A is a metric property, it's a property of metric spaces. So you don't really need to make things equivariant. So I just pick x0 in X. So this is some vertex. So this is x0. And now I will define this SXKL using this x0. So I take X, and then I consider the k-ball around X. So this is just k-ball. And for every element Y in this k-ball, I'll do the following thing. So the balls are, of course, combinatorial. And yeah. So for every Y, for every vertex Y, this is I mean, there is the so-called normal path. There is normal path from y to x0. And actually, this normal path is a sequence of simplices. So there is sigma 0, so this is just y, one vertex. And then there is sigma 1, and sigma 2, and sigma 3, and so on. And the last sequence, and the last simplex is x0, okay? There is a unique way of choosing a normal path. And actually, those normal paths resemble, in a way, normal paths of from K0 cubical complexes of Nibler reefs, right? So you could do it also for K0 cubical complexes, kind of. I mean, important thing is that maybe different thing that those are really simplices and they are at uniform distance. I mean, every such simplex lives in a sphere around this x0, actually in the level sets between those two. Okay, so there is this normal path. This is just given by the theory, and actually this is normal path. Similarly, as in K0 cubical complexes, those normal paths were used for proving biautomaticity of corresponding groups. And now what you do, you look at this sigma 6L. So L is this L. So let me just decorate this sigma by, let's say, y here, because it's going from y. And now I say that my SXKL is by definition the union of all the, because this should be a set of vertices, so just formally I will say that this is union of all sigma y 6L, where y goes over this ball. Okay. So you just pick all the y's. You consider the normal path. You pick the sigma y 6L. So those are all this lives in the level set, let's say 6L between x and x0. Okay. I'm sorry, I didn't. Yeah, actually, this is something to prove. Yeah, sorry, I should say. Okay, yeah, I didn't say this. Sorry, I cannot say this yet. I'm going to 6L. Yeah, I'm going to 6L somewhere, but I don't want to say for a moment more. Okay. So now, what happens? Okay, so we have this, and then so that's it. I mean, this is the definition of SXKL, and now I want to check that actually it works. So some points are trivial. Actually, the first, so I want to check the conditions 1, 2, and 3, because you see that it's finite sets and so long. So what about conditions 1, 2, and 3? So condition 1 is kind of trivial, because I just go k from x, and then I go 6L from this. So I'm still in a bounded ball. Uniformly bounded ball around x, right? So 1 is trivially satisfied. So checking 1, 2, and 3. So 1 is kind of trivial. 2 is also trivial. 2 just relies on the triangle inequality. So this one, this one is just about triangle inequality. I mean, either if you go d from x to y, then if you go d minus k from y, you are still in the ball of radius k, right? So this is just triangle inequality. And now 3 is the main condition that makes a problem. And it goes as follows. So for this, we need to prove a small lemma. of kind of independent interest for systolic complexes. This is equivalent. This is analog of the lemma for cut-zero cubical complexes. So there is a proposition. So we just prove it. So X is again systolic. And if you have two vertices at distance smaller than k, then there exists I bigger than 2k, such that for every j you have that the simplex in a normal path from y, so y is a distance x from smaller than k from x, so this y this simplex is inside the level set, inside of some level set between x0 and x. Okay, I should probably say something. So this is, I mean, so this proposition is the crucial, and actually this was my mistake when I started to explain it. So this says the following. If I take my my vertex y and I go by normal path, then of course this normal path, just by definition, I mean all the vertices in the normal path are in the interval between y and x0. Okay, but this proposition tells you that actually, if you are close to x, so if you are k close to x, then it's not only that you are that if you go far enough, then you not only are in this interval, but actually you get into interval between x and x0. Okay, so this is kind of like way of uniforming the space where after the 6L steps, and this 6L is actually, yeah, this is bigger than 2k, whatever. Then this is like uniforming where in which set you end up doing this procedure, and this is kind of important for this various proofs or properties that you use for property A, that somehow different things at large scale stabilize. Okay, so once again, whatever point I take here with this standard procedure, I end up with this in this one particular interval. Okay, and now if I end up in this one particular interval, then if I know that the level sets are, now I use that the complex is fit. So now fit implies that actually the number of elements in my SKL is actually bounded by some linear function. Okay.
So I missed, where do you stop with the normal paths?
I stop at 6L. So this is this particular L. Okay. Okay, I want to say maybe just polynomial. Okay, let's say polynomial. I mean, I want to make it, let's say, more generic to show you where the extension can go. Okay, and that's all. I mean, this is end of the proof. So basically I presented everything. I mean, this is just some combinatorial lemma. And so, any questions?
How are the normal paths chosen?
What?
So what's so special about those syntheses? You choose them.
I mean, if you know.
There's the whole interval.
What?
There's the whole interval. So.
Yes, there is a whole interval, but this is the same. This is the same in the case of cut-zero cubical complex, right? So maybe, I mean, if you have cut-zero cubical complex, I mean, you know, this theory of systolic and cut-zero cubical are somehow comparable in strange ways sometimes. But so if you have cut-zero cubical complex and you want to find the normal paths, Nibler-Riff's normal paths between two vertices, I mean, the interval is again huge. But one property is that there is like a single cube going down. And what you basically say, you take this single cube. I mean, you can rephrase it in different things. I mean, this can be path in one skeleton or path in some simplicial complex or path in cubes. So you take this one cube going down. You go to the vertex opposite. You have one cube going down, opposite. One cube going down, opposite. One cube going down, opposite. And this is path. So this is uniquely determined. And exactly the same happens in systolic case. Namely, if you have two vertices, then there is exactly one simplex going down, and you just pick it. And, okay, and it depends on the direction, right? This direction and this direction are different, but if you choose the direction, that it's unique. Okay, so this is the uniqueness. Okay, so maybe just last 2 minutes, let me just quickly mention the corollaries. So maybe just one. Actually, this was our motivating corollary. So corollary 1 for large type Artin groups and almost large type Artin groups. So are exact. So let me remind you that if you have a finite graph, so finite graph, simplicial graph, with edges labeled by numbers 2, 3, and so on, then the corresponding Artin group, so this is Artin, is the group given by presentation. You take the vertices of gamma and then you see the relation of the form VW, V, and so long, VW, VW, VW equal W, V, W, and so long, where here you take whenever you have a edge between V and W labeled M, and you take here M factors. Okay, this is the presentation. And then large type means that all M, all labels are at least 3. And almost means that you add also that there are no triangles with 2, so 2ML, or squares with 3 2s. M, let's say. And with Jingin, we showed that you can construct so there is a, let's say, theorem, large type or almost large type Artin groups act geometrically on systolic complexes. And it gives a lot of information about its geometry, so we proved it with Jingin Huang some time ago, and we used it for bioautomaticity and for other things. And also now we actually improve it to say that actually those complexes are phi. So this is and so let me just mention how this results compares to result of Jingin and Camille Orbes when they proved that two-dimensional Artin groups of hyperbolic type are exact. So hyperbolic types allows you to use some hyperbolic geometry. Large type in general doesn't allow you to do this. We do not know any reasonable hierarchy or whatever. And one important example is this group. So this is actually group, this is our large type Artin group that is not of hyperbolic type. So this is not treatable by their method. Yeah, by the way, this is actually commensurable to mapping class group of 5 punctured spheres. So it's known that it has property A. But there are simply bigger, much more complicated graphs that contain such trees, and because of this, you cannot treat them by this kind of hyperbolicity arguments. So we have to derive a new method for them. Okay, thank you very much.
Questions?
I just have a small comment.
Oh,
It might be worth adding, Damian. So might be worth adding that affine buildings are known to have property A. Just to add to your class, this goes back to 20 years ago, various people.
Yeah.
You and Sam McConnell and I forgot who else.
Yeah. So not only
Just to add to your list of. And I don't think it fits into any of this. They're not, typically they're not cubical complexes and they're not systolic, so it's sort of just a different class.
Yes, that's true. But actually, but actually, even more is known, namely all buildings. Buildings associated to Coxeter groups have finite asymptotic dimension. And then for proving, and finite asymptotic dimension is then stronger than property A, so it should be said here. There is this is finite asymptotic dimension, so it's finite. So even for all buildings, it's known that they have property A. Yes, I should maybe include it, but yeah, that's true. But there you use particular geometry of buildings, so yeah, in a sense it's more amenable. But yes, that's true. And actually, we want to extend our research, our result to finite asymptotic dimension. So, thank you very much.
Yeah, I have a comment on the large type. So actually, there's a lot of hyperbolicity in large type Artin groups. So for example, if you look at Deligne complex, then it's relative hyperbolic to these 333 things.
Okay.
So if you know the 333 things exact, maybe you can use the relative hyperbolicity to do something. So that could be possibly another path.
Okay.
Yeah.
Thank you.
So the Deligne complex, not the Artin group itself. So.
Okay. Thank you.
So for property A, you don't really need the co-compactness of the action, just property.
Yeah.
Would it be maybe more Artin groups act properly on this node?
I don't know examples.
An example of something systolic that is not fit a group.
Yeah. Yes. You can build them, or there is, one example of systolic complexes come from the so-called C6 small cancellation groups. So this is kind of the most standard one, and so this is Danny Weiss construction. So if you have C6 small cancellation groups, C6 in fact small cancellation complex, you can associate to each systolic complex. And we observe that this complex can be not fit easily. Yeah, actually, it's good that you have this question. Well, actually, I also asked Sophie to suggest to me responses to questions. So I should start like, that's exactly the kind of question that kept us up at night. This is there are more. Okay, but so what I want to say is that this also refers. This relates to this similarity to cat zero cubical complexes. So somehow for cat zero cubical complexes, actually the original proof of property A of cat zero cubical complexes uses the fact that intervals in cat zero cubical complexes are like subcomplexes of Z to N. This is very important. So in fact, they grow very slowly, simply. It's totally different in systolic complex because they can be this tree-like stuff. And this can happen here, for example. So yeah.
Any further questions? Okay, let's thank Damian and both this afternoon's speakers one more time.